Hi, I'm Alessandro Ferrero and I'm Professor of Electrical Measurement at Politecnico di Milano University in Italy. This tutorial is aimed at finding an answer to one of the most critical problems of the measurement science and practice. How can we evaluate how good are the results we get from our measurement procedures and instruments? To find an answer, we'll analyze the following points. First of all, we need to establish how good our measurement shall be. To do so, we need a model for the measurement process, and this model must be capable of identifying the sources of inaccuracy and explaining their effects on the measurement results. So, starting from this model, we can define a way to quantify the quality of a measurement result. I'll briefly discuss the old error concept, and then I'll cover the more modern uncertainty concept, discussing its definition and the way it can be evaluated. At last, I'll spend a few words on the traceability concept and also on some open issues of which measurement practitioners must be aware. So, let's start with the first point. How good shall our measurement be? Very often, we listen to non-expert people stating that the better is the measurement process, the more accurate is the information we get. However, is this really true? How far can we improve our measurement process? Is it worth the cost? And above all, can we ever get the exact value of the measurement? Well, these are the fundamental questions of the measurement science. To find an answer to them, we need to understand, first of all, how the measurement process works. And let's try to sketch a model for it. Well, a good definition for a measurement process models it as the quantitative comparison of the quantity to be measured with another quantity, which is homogeneous with the measured one and is considered as the measurement unit. To be honest, this definition applies only to the measurement of physical quantities. However, if we relax a bit the traditional concept of measurement unit, it is possible to apply it also to the measurement of non-physical quantities. In any case, this definition is quite perfect for our purposes, so let's consider it. Now, if we try to represent this definition in a graphical way, as in this new slide, we realize that the measurement process can be described by the interaction of 5 agents. The measurement, here, that is the quantity under measurement. The standard, here, that is the physical realization of the measurement unit. The method, that is the theoretical procedure we adopt to compare the measurement against the standard. And then the instrument, that is the device that implements the measurement method. And at last, but of course not least, the operator that supervises the measurement process and reads and interprets the measurement result provided by the instrument. Let's now go back to the fundamental questions we talked about a few seconds ago. The main one is for sure the one concerned with the capability of obtaining from the measurement result the true value of the measurement. The answer to this question is of course negative, and if we look into each one of the 5 agents, we can understand why this answer is negative. So, let's start with the measurement. Very often, our knowledge of the measurement is incomplete. We model it with a mathematical model that is generally only approximated and sometimes not totally correct. Furthermore, the state of the measurement at the measurement time is not completely known, and the measurement process modifies its state. If we now consider the standard, we realize that it is generally a good realization of the measurement unit, but not an ideal one. So it can provide only an approximation of the measurement unit. The theoretical method we adopted to perform the comparison between the measurement and the standard is generally based on a physical phenomenon, let's say electromagnetic interactions, electromechanical interactions, as in the old instruments, and so on. However, other phenomena do generally interfere with the considered one, So the actual result of the comparison might differ from the expected one, and hence its interpretation can't be totally correct. Then we have to implement the comparison method in a real instrument. Here too, the actual operating principle differs from the ideal one for a number of different reasons. Let's say non-ideal components, internally generated noise, sensitivity to environmental conditions, lack of calibration, age, and many others. And now we come to the operator and his or her role in the measurement procedure. Just to mention a few critical points, measurement execution must be just in time. Of course, if the measurement conditions are evolving, it's important to relate the measurement result to the corresponding condition. Let's speak about parallax errors that must be carefully avoided when reading the displacement of a pointer on a ruler. Well, this is a very common error among inexperienced operators. The operator must interpret the measurement results in a correct way, as well as post-processing them correctly, and so on. As you see, it's a very important and critical role that might affect the quality of the measurement result in a quite significant way. And finally, there is the rest of the world that influences the whole measurement procedure. It's the effect of the so-called influence quantities. We have electromagnetic interferences, temperature variations, mechanical stress, and a number of other environmental effects, more or less significant, depending on the different kinds of measurements we are performing, that may influence the procedure and affect the final measurement result. Well, until now, we have simply discussed the different possible reasons that may cause the measurement result to differ from the measurement value. We haven't yet mentioned the implications that this fact has on all actions we may take, and the actions that we may take based, of course, on the obtained measurement result. This is a very important point too, because it lets us understand how important measurement accuracy is. If an inaccurate measurement doesn't affect our subsequent actions, then we can somehow disregard these issues. Otherwise, we can't. So, the best way to understand these implications is to consider repeated measurements of the same quantity. Because of the reasons I mentioned in the previous slides, if we repeat a measurement procedure several times, the measurement values that we get will differ from each other, even if we don't change the measurement conditions. What happens is more or less the same as what happens when we shoot to a target. Each new arrow or bullet will hit the target in a different position from the previous ones. If we are good archers or good shooters, we obtain a very tight burst pattern around the center of the target, but we'll never hit exactly the same point with all our arrows or bullets. Furthermore, if the measurement procedure is repeated by another operator who reproduces the same measurement conditions somewhere else and with different instruments, although maybe of the same type as our ones, different results are obtained again. Coming back to the example of the shooter, a different shooter will create a different burst pattern than the one we created. Well, at this point we can draw a first conclusion. We can't express a measurement result with a single value because this is meaningless. This same value will be barely obtained by a new measure. This has a first very important implication. We can't use this single measurement value in any comparison. Since all measurement results are different, we would be forced to conclude that, for instance, the mass of an object measured in Milan today is different from the mass of this same object measured in any other place at the same latitude and height tomorrow. Well, you can easily understand that this is not acceptable. The most frequent application of a measurement result is in a comparison process. Think, for instance, to the pass or no pass decision in an acceptance test. Therefore, we must solve this problem. how can we still represent the result of a measurement with a single value and avoid the drawbacks that I mentioned? The question is this possible? So, this answer is positive, but we must find a way for assessing how good the measurement result is. In other words, since we understood from our model that the result of a measurement can only approximate the measured value, we must find a way to quantify how good this approximation is, or, if you prefer, how complete or how incomplete is the information we get from the measurement result about the measurement. The most immediate way is that of representing the measurement result with an interval of values instead of a single value, within which we may expect to find the value of the measurement. In the past, and let me add that it's a recent past, this interval was defined according to the error theory. This theory is based on the assumption that the true value xt of the measurement is somehow known. Then, if xm is the measurement result, the absolute error is defined according to this relationship here. So it's the difference between the measured value and the true value. If we consider that the maximum error, we can build this interval about the measured value, within which the measured value is supposed to lie. Here you see the measured value minus the maximum error, and the measured value plus the maximum error. So, this approach raises a big philosophical question. We have seen that the measurement results can provide only incomplete knowledge about the quantity we are measuring. So this knowledge is incomplete. And if it's incomplete, how can we ever know the true value of the measurement? Well, this is the main flaw of the error approach. The true value is unknown. Moreover, it can't be known because all measurement processes, even the best ones, are not perfect and provide the result that differs from the true value. And to make things even worse, the existence of the true value can't be assumed even from the theoretical point of view, in many cases. This is the typical situation of quantum physics, where the measurement can be often represented only by a probability density function. So, we can bury the error theory under the heavy stone of the unknowable true value. And we still have the problem of defining how close a measurement result is to the unknown measured value. More recently, in the late 80s, a new concept was introduced, that of measurement uncertainty. Uncertainty was introduced as a quantifiable attribute of the measurement, able to assess the quality of the measurement process and result. As you can see in this slide, this concept has been introduced because of the awareness that when all the known or suspected components of error have been evaluated and the appropriate corrections have been applied, there still remains an uncertainty about the correctness of the stated results. That is, a doubt about how well the result of the measurement represents the value of the quantity being measured. Just to have an idea on how this concept evolved in time, it has been considered in 1992 by the International Organization for Standardization, the well-known ISO, for the first time in an official document, the Guide to the Expression of Uncertainty in Measurement, also universally known as GAM. This guide has been recently encompassed in several standards issued by national standard organizations, such as, for instance, the Italian UNICEF, the German DIN, the French AFNOR. Let me add that the uncertainty concept was proposed for the first time by the International Vocabulary of Basic and General Terms in Metrology, the well-known VIM, 8 years before the GAM was published. We were in 1984. Well, we have set the uncertainty concept in its historical background. Let's now discuss its meaning. the international vocabulary in the guide define it as a parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurement. So uncertainty is expected to somehow quantify the dispersion of the values that could be assigned to the measurement. But how can we do this? Well, the key point in this definition is adverb reasonably. It signifies us that our capability of quantifying this dispersion in a reasonable way depends on the amount of available information we have about the measurement process and the results. Let's comment this point a bit more in details. If we look at the etymology of the word uncertainty, we realize that it means doubt. Thus, uncertainty of measurement means doubt about the validity of the measurement results. However, I don't like to approach uncertainty in this strict etymological way, although the VIM and the GAM do this. But doubts have a sort of negative implication, as if we can never solve them. On the other hand, if we succeed in quantifying uncertainty, most of our doubts will dispel and we refine our knowledge about the measurement. Therefore, I prefer to interpret uncertainty as a way to reflect the lack of exact knowledge about the measurement. You can understand that if we find a way to quantify it, then we improve our knowledge of the measurement. In any case, one conclusion can be drawn. The certainty of the old error approach has vanished. Now, we have defined and commented on this new concept. We still have to understand what uncertainty should provide. The guide answers to this question once again. Let's read it. In many industrial and commercial applications, as well as in the areas of health and safety, it is often necessary to provide an interval about the measurement result that may be expected to encompass a large fraction of the distribution of values that could reasonably be attributed to the quantity subject to measurement. So we need an interval. Again, the definition of this interval is quite vague. The interval may be expected to encompass a large fraction of values that could reasonably, again, this adverb you see, that could reasonably be attributed to the measurement. So if we want to use this concept in practice, we must be less vague about this interval, and we must have a stricter mathematical definition. And the GAM helps us again. Here is what it says. Thus, the ideal method for evaluating and expressing measurement uncertainty should be capable of readily providing such an interval, in particular one with a coverage probability or level of confidence that corresponds in a realistic way to that required. Oh, this is much clearer. Uncertainty should provide an interval of confidence with known level of confidence. If we have this data, then we can eventually assess whether the obtained interval corresponds to that required in a realistic way. Well, now we know how to proceed, because we know the problem. The result of a measurement provides only incomplete information about the measurement. We know what to do. We need to refer the uncertainty as a parameter to be associated with the measurement result to characterize the dispersion of values that could be attributed to the measurement. And we know what should be obtained, a confidence interval about the measurement result with known level of confidence. Please note that sometimes the required level of confidence is set by some requirement imposed by the application that uses the measurement result, and we must be capable of defining the correct interval. Now, the only problem left is the evaluation of uncertainty. We talked about an interval of confidence with a known level of confidence. But if we express uncertainty with a standard deviation or a given multiple of it, we can readily find this interval. Let's see how. Let's suppose that the measurement results are distributing according to a normal distribution, as for instance the one which is shown in this figure here. Well, if we express uncertainty with the distribution of standard deviation sigma, then we can build an interval, here it is, about the measured result x bar here, and x bar is of course the distribution mean value, ranging from x bar minus sigma to x bar plus sigma. And we know that the probability of that the measured value falls within this interval is the 68.3%. If we now express uncertainty as 3 times sigma, we have this larger interval here, and the probability climbs to the 99.7%. Well, if we consider the operative way we can follow to evaluate uncertainty, we may evaluate it from the statistical distribution of the results of a series of measurements and characterize it with the experimental standard deviation. Of course, this method can be applied whenever a significant number of measurement results can be obtained by repeating the measurement procedure in the same measurement conditions. On the other hand, if this is not possible, uncertainty may be evaluated from assumed probability distributions, where the considered assumptions are based on experience or other available information. Also in this case, uncertainty can be characterized by a standard deviation. In fact, let's suppose that the confidence interval is known a priori, for instance because it is provided by calibration results. In this case, we may assume a suitable probability distribution over this interval, and the most employed are the normal or the uniform distributions, and then evaluate the corresponding standard deviation. Let's see an example. Let's suppose that the calibration results provide the confidence interval shown in this slide. Here it is. In this case, here it is. In this case, we usually assign a 100% level of confidence to the interval. Let's now assume a uniform probability distribution over this interval. According to statistics, the resulting standard deviation is A, so the half amplitude of the interval, divided by the square root of 3. Well, we have discussed the concept and the meaning of uncertainty. Let's now go quickly through some definitions and terminology. We refer to standard uncertainty whenever uncertainty is expressed as a standard deviation. We refer to a type A evaluation of standard uncertainty when we evaluate the standard uncertainty through the statistical analysis of a series of observations. Of course, we must be able of collecting a statistically significant number of observations to apply this method, and this is not always practical or cost-effective. So, on the other hand, we refer to a type B evaluation of standard uncertainty when we evaluate the standard uncertainty through any method other than the statistical analysis of a series of observations. Of course, this method has to be applied whenever, for any reason, we can't collect enough data from our observations. And the required standard uncertainty value when type B evaluation is adopted can be obtained from previous experience, a priori knowledge, or any other relevant available information. Let's go on with our definitions, and let's see that we refer to the expanded uncertainty whenever we want to refer to a quantity that defines the interval about the result of a measurement within which the values that could reasonably be attributed to the measure may be expected to lie with a high level of confidence. Well, of course, we have to state how high this level should be according to the requirements of the specific application we are dealing with. But once we know the desired level of confidence, then we still have a problem in defining the correct interval to this level. In fact, to do so, implicit or explicit assumptions are needed about the probability distribution defined starting from the measurement result and its standard uncertainty. It is well known that we can attribute a specific level of confidence to an interval only if we can locate this interval inside a known probability distribution. So we can conclude that the level of confidence that can be attributed to the interval defined by the expanded uncertainty can be known only to the extent to which the assumption about the underlying probability distribution is justified. And this is a very important point that is often neglected in practice. We have one last definition. We define coverage factor, the numerical factor used as a multiplier of the standard uncertainty to obtain an expanded uncertainty. And let's see the symbols and then the notation that is used in the measuring practice. As you can see, standard uncertainty is represented with a small letter u, the coverage factor with a capital K, and the expanded uncertainty with a capital U. Let's now consider a few examples. Let's suppose that we are measuring a DC voltage with a 5-digit multimeter. We are using the 10-volt range, and let's suppose that the instrument reading is 7.2587 volt, as shown in the slide. We wanted to evaluate measurement uncertainty, and the only available information we have comes from the manufacturer's specifications. Of course, according to our previous considerations, we have to follow a type B evaluation method. So, let's see the manufacturer's specifications. In this slide, you have a typical example of specifications for, here they are, you see, for DC measurements and the different possible ranges that are listed here. We select the range of interest, and we suppose that we are using the instrument within 6 months from last calibration. So these are the data of our interest. The manufacturer's specifications in this case provide an interval about the reading whose half amplitude is given by 0.02% of reading plus 6 digits. Therefore, we can compute this half amplitude A as shown in this slide. Now, according to our considerations, we have to evaluate a standard uncertainty, that is, a standard deviation of a probability distribution. Therefore, we need the distribution of the interval we have obtained in the previous slide. And our problem is that we don't know anything about possible distribution of the possible measurement results. Remember that these are our starting assumptions. We have only the manufacturer's specifications and nothing else. By the way, this situation is very often met in practice, not to say that it's probably one of the most frequent situations. In this case, we may refer to the maximum entropy principle and assume a uniform probability distribution over the obtained interval. We know that the standard deviation of this probability distribution is given by its half amplitude divided by the square root of 3, and our standard uncertainty is the one shown here in the slide. Here it is, 1.18 millivolts. Let's now consider another example. Let's suppose that we are measuring a DC voltage again with the same 5-digit multimeter. Let's suppose that we are still using the same 10-volt range, and let's suppose that now we can repeat the measurement procedure several times. Therefore, we can follow a type A evaluation method. Let's suppose to read the values shown in the slide. You see, we have a number of values. Actually, there are not too many, but only to have them clearly shown on a single slide. We can now make some computations on these values. We can compute the average value, as you see here in the slide, and this average value can be taken as the best estimate of the measurement value. Then we can compute the experimental standard deviation, here it is, and obtain this value. And having adopted a type A evaluation method, the standard uncertainty is by definition the same as the experimental standard deviation. As you can see here in the slide, here it is, the standard deviation, and the same value is the standard uncertainty. So, let's now make a further step, and let's suppose that we have the manufacturer specifications and we have also the results of repeated measurements. Let's also suppose that the numerical results are the same as in the previous examples. It is quite immediate to suppose that the final uncertainty might depend on the experimental dispersion of the measurement results and on the instrument features that are expressed by the manufacturer's specifications. And this is quite likely to occur in practical situations, and therefore the best evaluation of measurement uncertainty should take into account the values obtained by applying both type A and type B methods if available. And this can be done by combining in a statistical way the standard uncertainty values obtained in the two previous examples. And the result is shown here in the slide. You see the statistical combination and the final result. So, until now, we have considered only single measurements. However, we shall consider another important problem. Very often, the value of a quantity to be measured is obtained from a mathematical computation of the results of other measurements. Just to mention two simple and frequent examples in the electrical field, this is the case of the electric power under DC conditions and the impedance of an electrical load, as you can see in the slide. Both of them are computed starting from measured value of voltage and current. So the problem now is, once we have evaluated the uncertainty on the single measured values, voltage and current in these two examples, how can we evaluate uncertainty on the final measurement results? Once again, the guide helps us. In fact, it introduces the concept of combined standard uncertainty. Let's see how it is defined. So, the GAM states that the standard uncertainty of the result of a measurement, when that result is obtained from the values of a number of other quantities, is equal to the positive square root of a sum of terms, being the variances or covariances of these other quantities, weighted according to how the measurement result varies with changes in these quantities. And starting from the combined standard uncertainty, the combined expanded uncertainty is then evaluated in the same way as that followed with direct measurements of single quantities. Well, I'm almost sure that this is absolutely not clear to you, and it's not clear as any definition based on a mathematical relationship when we try to express it in words instead of expressing it with suitable mathematical symbols and equations. So let's try to better understand what the GAM wants to define just by putting these words in symbols and equations. So let's assume that the result y of the measurement depends on n other measurement results that we call x sub I, where I ranges from 1 to n. Let's suppose that this dependence is expressed by the functional relationship shown in the slide here. I can get the pointer. Here it is. So let's also assume that the standard uncertainty of each result, x sub I, has been evaluated. And the way the combined standard uncertainty is computed depends on whether the input quantities are correlated or not. Let's suppose to start with that the input quantities are not correlated. And in this case, this is the mathematical relationship that expresses the definition of the combined standard uncertainties. You can easily check that it is a positive square root, and it's the square root of a sum of terms being the variances, in this case, of these other quantities. And here you see the variances. Here they are. The square of the standard uncertainties of each measured values are variances, since the standard uncertainties are standard deviations by definitions. So here they are. Now, the given definition also says that these variances are weighted according to how the measurement results varies with changes in these quantities. And here you can see the weights. They are the partial derivatives of function f that here act as a sensitivity coefficients and show how the measurement result varies with changes in each single quantity x sub I measured directly. Now, let's consider the case of correlated input quantities. In this case, the mathematical relationship that expresses the definition of the combined standard uncertainty changes as shown in this slide. You can still see the weighted sum of variances here. Here it is. You see, as in the previous case. In this case, you can see also the weighted sum of covariances as mentioned in the definition by the guide, and the weights are again the partial derivatives of function f. So usually the correlation coefficient is used to express the degree of correlation between two quantities x sub y and x sub j. The correlation coefficients can be expressed in terms of variances and covariance as shown in this relationship, and it takes always values between -1 and +1. If x sub e and x sub j are independent, the correlation coefficient is 0, and if they are totally correlated, it becomes equal to 1, as you see here. So if you use the correlation coefficients in the previous relationship instead of correlations, then the combined standard uncertainty is given by this relationship here, that is perfectly equivalent to the previous one. It's just a bit more convenient to use, since it is written in terms of only the standard uncertainties. Here you see them, here and here, associated to each single measurement result, and here it is the correlation coefficients. You can immediately check that when the input quantities are not correlated, that is, when all R coefficients are nil, this relationship becomes exactly the one we found for uncorrelated input quantities, because this part becomes 0, identically 0. So to better understand how these relationships are used, let's consider a couple of examples. Let's consider first the measurement of DC power. Let's suppose that we measure DC voltage and current with two different multimeters. Let's suppose that V sub m and I sub m are the measured values. Then the desired power value is given by their product as shown in the slide. We also suppose that the only available information is given by the manufacturer specifications, and therefore we have to follow again a type B method to evaluate uncertainty. Let's suppose that the readings are those shown in this slide, where you can see also the ranges set on the instruments. Of course, the measured power takes the value shown here. And let's consider the same instruments considered in the previous example. So, same kind of manufacturer specifications. Let's also follow the same procedure for evaluating uncertainty. So we find that voltage uncertainty is 1.27 millivolts. Similarly, again, we show the manufacturer specification for the selected current range, and the current uncertainty here is 26 microamps. Now, let's remember that we are using two two different instruments for measuring voltage and current. Under this condition, we can also assume that the two measured values of voltage and current are not correlated at all, because the two instruments are different. Different history, totally different. So let's compute the waving coefficients as shown here and the partial derivatives of function p against v and I, and finally we obtain the combined standard uncertainty for the measured power value, applying the relationship we have seen a few slides ago. And here is the value, 218 microwatts. Now, let's suppose to use the same instrument for both voltage and current measurements. This is also possible since there are some multimeters that have voltage and current input channels that can be used simultaneously. In this case, the measured voltage and current values can't be supposed not correlated. On the other hand, they are likely totally correlated. We are using the same instrument, so that their correlation coefficient is 1. For the sake of simplicity, let's suppose that the numerical values are the same as those in the previous example. Let's use these values in the combined standard uncertainty formula. Here it is, where the correlation coefficient here is 1. And this time we get a combined standard uncertainty of 272 microwatts. So, as you see, this procedure is relatively easy to apply, at least when the number of quantities involved in the measurement process is not high. However, the definition of the combined standard uncertainty has some underlying assumptions that must be considered to avoid big mistakes. So, here is the formula again. And do you know how it has been derived? I have not said this yet. Let's see. It's simple. It comes from the Taylor series expansion of the relationship linking each measured quantity to the final measurement results. And this series expansion is truncated to the first term. So the formula is valid only when function f here is linear and its derivatives exist. Well, this assumption seems quite strict, but it's also quite plausible. Since usually measurement uncertainty is small, we are considering only small variations around value y, and it's generally possible to consider function f linear within this small range of variations. In general, we also consider continuous functions, usually consider them, and hence we can assume the existence of the first derivatives. But there is another, more important assumption that we must consider. This relationship provides the combined standard uncertainty. Remember, it's a standard deviation here. And it provides this combined standard uncertainty starting from the standard uncertainties, here they are, here and here, that we get from each measured quantity. We know that the standard uncertainty is useful because it allows us to define through a suitable coverage factor a confidence interval. But we have seen that this is possible only if we know the probability distribution associated with the measurement result and its standard uncertainty. So the question is, which is the probability distribution associated with y? Unless we start from very few input quantities x, and the probability distributions associated with them are quite simple, it's not easy to compute the probability distribution associated with y. At least it's not easy to find a closed form way to compute them. So we need to refer to the well-known central limit theorem that states that when f is a linear combination of the input quantities and none of them is prevailing on the other ones, then the final probability distribution tends to a normal one, as the number of input quantities tends to infinity. Of course, this is not generally the case in practical conditions. So the final distribution is only an approximation of the normal distribution, and it's as good an approximation as close we are to the assumptions of the central limit theorem. In conclusion, we should never forget that the validity of this relationship here is limited by the validity of the underlying assumptions. If we are far from satisfying them, the value we get for the combined standard uncertainty can be a quite wrong estimate of the measurement uncertainty. And we must always keep in mind this fact. So, let's now check if the uncertainty concept helps us solving the problems we talked about at the beginning of this tutorial. Do you remember that I said that the measurement results are almost always employed in comparisons? Well, let's see the role of uncertainty. So, we can state that the two measurement results are considered equal. Well, actually, it's preferable to say compatible, since we know that they can't be equal in a strict mathematical sense. So, they are compatible if the confidence intervals associated with them and expressed by the expanded uncertainty, as you see here, are at least partially overlapping, as shown in this figure. And now, let's see an example of measurement results that is not compatible with the two other ones, because, as you see, the confidence interval in red here doesn't overlap the two other ones at all. So x1 and x2 are compatible, x1 and x3, x2 and x3 are not compatible. Well, mathematically speaking, this concept is expressed by this relationship where x1 bar and x2 bar are the maximum likelihood values for the measured quantities x1 and x2. Well, they are the central value of the confidence intervals we have considered. The U values are the standard uncertainties, cov is the covariance, and k is the coverage factor. So the two measurement results are compatible when their distance, which is given by this relationship, well, this distance is lower than this quantity that is related to their expanded uncertainties. Well, now I expect you to ask me a question. The methods we have discussed until now compare confidence intervals, or the distance between maximum likelihood values. But how is it possible to ensure that the maximum likelihood values and their associated uncertainty to really characterize the dispersion of values that could reasonably be attributed to the measure? In other words, how can we be sure that we don't define an interval here and the measurement values falls there? This is another big problem. So the answer to this question can be found in the role played by the standard. Do you remember that we considered the standard in our model of measurement process, and then we have not mentioned it until now? Well, it's time to consider it. Any measurement result must be traced back to the value of the standards involved by that particular measurement. This procedure is called instrument calibration. We can implement it in two ways. It can be performed by direct comparison with the standard, that is, measuring the standard with the experimental setup employed in a particular measurement procedure. Theoretically speaking, this is the best way, but it's generally very expensive, and let's say that the waiting lists are quite long. The second way is to perform an indirect comparison with other instruments that have been calibrated. In this case, the uncertainty value assigned to our measuring system is higher than in the other case, but the calibration is faster and usually much cheaper. from the technical point of view, since in the end the measurement result must be traced back to the standard. It requires an uninterrupted chain of comparisons, and the standard must be found at the end of the chain. Well, we have covered all most important issues related to uncertainty in measurement. We have understood that measurement results provide always incomplete information about the measurement. We have seen how the approach in terms of uncertainty allows us to quantify how incomplete this information is. We have seen that this approach has been encompassed in an official guide, the GAM, and this guide refers to the mathematical theory of probability as the main mathematical tool to handle incomplete information. According to this approach, uncertainty is expressed as the standard deviation of a suitable probability distribution. So, everything looks attractive, looks working, looks effective, at least from our examples. But there is still one question left. Is there any price to pay to this approach? The answer is yes, there is, and we must be aware of the cost. Let's see why. So, the first tribute to pay to this approach is that the systematic effects must disappear. This is clearly stated in the GAM. Let's read it. It is assumed that the result of a measurement has been corrected for all recognized systematic effects, and that every effort has been made to identify such effects. Well, this requirement is quite obvious, since probability handles random effects and not the systematic ones. The second tribute is related to the fact that, as we have already discussed, the dispersion of values that could be reasonably attributed to the measurand is always described in terms of a distribution of probability. This distribution is described in terms of its first two moments, mean value and standard deviation. And if we want to use only these two values, then the distribution must be known, either because it has been determined experimentally or because it has been assumed a priori. Well, this is relatively simple to do when we consider a single measurement. But what happens when we have to deal with indirect measurements? Well, we have two ways to associate the probability distribution to the combined standard uncertainty. The first way is to refer to the uncertainty propagation law and refer, of course, to the assumptions that are behind this law. And we have already discussed these assumptions. The uncertainty propagation law comes from a Taylor series expansion truncated to its first term, and the central limit theorem is applied to assume that the final distribution is a normal one. And we have seen that these assumptions are not always satisfied. And if they are not, the only way to estimate the final probability distribution is through a Monte Carlo simulation. This is suggested by the supplement 1 of the guide, but it's a time-consuming method, and everybody knows that it might show some convergence problems. But now, let's go back to the main drawback. It's again related with the systematic effects. The GAN requires that they are not present, or if they are present, they must be identified and properly corrected. So, the problem is that the systematic effects do exist. It's not always possible to identify them. It is not always possible to apply the corrections. But even when it is possible, even when it's possible to identify them, it's possible to apply corrections. It is often not convenient to apply them, because corrections take time and money, and uncertainty reduction is not always worth the cost, at least in many practical situations. Let's see a very simple but also very meaningful example. So, the double weight method is the best known example about the correction of systematic effects. It's explained in every textbook of measurement. In this case, in this example, the systematic effect is due to the different lengths of the two arms of a balance. So, let W1 be the measured weight with the known weights on the left pen and the unknown weight, in this case it's a diamond, on the right pen. Now, let W2 be the measured weight when we exchange the position of the known weights with that of the diamonds. To correct the effect of the different lengths of the arms, we must compute the average of the two measurements, as you see here. It's very, very simple, and this is surely worth the cost of the correction and the time we take to apply this correction due to the value of the diamond that we are weighting. Yes, but are we sure that it is still worth the cost if we are weighing potatoes? I'm sure you don't have doubts about the correct answer. The point is that in less evident cases, we must be capable of evaluating uncertainty also in the presence of systematic effects. Let me say, also in the presence of unidentified and uncompensated systematic effects. And we need this to assess whether correcting systematic effects is worth the uncertainty reduction or not. And if we do not evaluate uncertainty under these conditions, we cannot assess this, and we don't know what to do. We don't know what is more convenient to do. So there is no doubt that the probability theory is a very efficient tool to handle incomplete information whenever random phenomena are involved. But the true question is whether there is a better tool to handle incomplete information when also non-random phenomena are involved. Right now, there is not yet a definite, totally agreed upon answer. However, a recent mathematical theory has been developed to generalize the probability theory and appears very promising to represent uncertainty also when systematic effects are present. This theory is the theory of evidence and has been formulated by Glenn Schaffer in 1976. Very recently, it has been applied to express and process uncertainty in measurement. And you can find a very interesting report of this approach in another book, that of Simona Salicone. As you see, there is still a lot to work on measurement uncertainty to gain a better knowledge about our measurement results and advance in the fascinating field of the measurement science. And this concludes this tutorial. I hope you found it useful. Thank you for your attention, and goodbye.